I would like to introduce you to today's presenter. Dave Nelson is one of our applications engineers from our Omaha, Nebraska office. Some of you may know Dave from either training at your facility or one of our training classes in Omaha. Take it away, Dave.
Okay, thank you. As I believe was mentioned, if you did miss the first two parts of this series, you can still catch them if you go to Productivity's website. It's productivity.com/webinars. And of course, this one is on macro programming, and this is a very large subject. So I want to point out that I'm not going to be able to cover everything in the short time that we have together, but we do have classes on this. So if you are interested in learning more, we can set up a class, or we have one scheduled that you can attend. Also, there are some manuals for you. One of them is the programming manual for the Renishaw probe, and the links are kind of long, so I just put up here a Google search. If you go to Google and search for Haas Renishaw probe programming manual, you will find this document. Plus, the manual itself that comes with the machine is very handy. And if you don't have one, or if you want one that's in PDF form so you can have it on your computer or something, there's a link for that one as well. So some of the things that I'm trying to do by doing this webinar is to help you get the most out of your machine's capability. We kind of did that on the previous webinar, where we used capability that was already at the machine, stuff that we were already familiar with, to leverage the ability to produce in-process probing. And that's a primary concern of mine as I go through this, to try to get you the tools that you need to get to use them right away. And we'll cover components of macro programming. We're going to talk about things like subroutines and variables and so forth. And that's the primary part of this, is that we use variables and we use subroutines to produce the kinds of functions that we are after. We're going to use variables to set offsets directly, and instead of using probing, or instead of typing in values or setting them in a manual manner, we can actually write directly to the variables through macros. And then we'll also look at using the Renishaw cycles directly instead of using the conversational programming that Haas has on their machines, and the benefits of those. Now, one of the things that I want to start with here, though, is an issue that I've had in the past, where if you are using the machine's counter, if you're making a couple thousand parts or something, and you want to have a parts counter, and you didn't reset it before you started, you started running and you didn't reset it at that point, so you'd have to set that counter to a certain number. So if it's wrong, then how do I fix that? And you're probably familiar with seeing the timers and counters on your machine, and notice that you have M30 counters. And in this case here, I have 157, but I made a couple parts, or I made a few parts, and it's incorrect. Okay, so I need to have it be 155 maybe, or whatever it might need to be. I can actually type this in, pound 3901 equals 155, and run that in MDI, and it would change this first counter to 155. And where do I get that information? How do I know that 3901 is that counter? Well, in your Haas manual, under the macro section, you will find a page that lists all the variables, and you can see that 3901 is the M30 count, and there's, of course, 2 of those. And I find this to be an extremely helpful thing. If you don't have macros on your machine, and with probing, of course, you do, but if you didn't have macros on your machine, you wouldn't be able to set this to any value. All you could do would be to zero it out, and that may not be what you want. So this is a nice, easy way to fix that problem. And it's counters that are of interest here that we can use and make our own counters or use this one. And it's a nice feature that we can have through using variables. And we'll look at that as we go along. But before we get into counters and setting work offsets, let's look at tools again. And if you're familiar with if you watched the second in the videos here where I showed you this video here. Sorry, get myself situated. We'll run this. So if you go to the tool offset page on the next gen control, and if you've filled out all the information that you need, you can actually just press tool offset measure and you can initiate touching off all your tools. In this case here, I just have 3 of them being set. And what you see on the screen here is the code that that you would get, and it would show up in MDI. So first we touched off a drill. Now we're setting an end mill. This end mill is going to touch off the length. And it's going to do the diameter. It's going to go back on the center. Touch off one side. I want to point out that this is a really powerful tool that if we take the time to make approximate measurements of length and diameter and set the values in the offset page, and all that an operator ever has to do is go into the offset page, press offset measure, and you can begin touching off either an individual tool or all the tools that have been set up, ready to run. So here's our face mill. This one is just going to shift off center, spin, and it's only. Okay. So when we ran that with the tool offset measure key, we get this bit of code in MDI, and that's all that I'm showing up at the top there. So this is fine. We can take the time and plug those information in there manually, but what I want to show you is that we can get all this stuff done in advance. And if you have watched any of the Haas tip of the day videos, you may have seen this sheet. This is a little cheat sheet that shows what variables are associated with certain parts of the tool data. And I think it's important to begin to think about this page, the offset page, the tool offset page, as tool data, not just offsets. So in this case here, we have this column that's approximate length, and you see the variables that are associated with it. So tool 1, it's pound 51,801, and then 802 for tool 2, and so on down the line. And we also have approximate diameter and the edge measure height. And this particular column is for using with ball end mills or bowl end mills or face mills where there's a 45-degree lead. You can actually specify how far down the tool has to go to measure the diameter, if that's something that you are going to do. And then finally, on this column over here, we have the probe type. And what they mean by this is the probing cycle that we're going to run. So if 0 is in there, then there's not going to be any probing done. If 1 is in there, then the length probing rotating cycle will work. So like what you saw with the face mill was set to 1. If you are touching off a drill or a tap or a small end mill, something smaller than a 1/2 inch, then you probably just need to do length probing non-rotating. So that's going to be the quicker of all of them. And then finally, if you want to get both length and diameter, then you would put 3 in there. And that's what we used for the 1/2 inch end mill that you saw earlier. So we plug all that information in, and this is what it would look like. And I just want to point out, just kind of review this, that we can clear out a column. So if you wanted to clear this out, you can go in here and hit origin, and then you can press 2 and it would clear out this whole column. Or if you wanted to clear out one tool, you can press 3 and it would wipe out everything in that row. But I want to show you now what the code looks like, what we do to set these things in advance. So the operator doesn't have to punch it in, we can actually put it in our program. So I'm just going to take a look at what that looks like here. So here we have 3 tools that we're going to set, and we have, I'm calling it tool data here, and I put tool 1 in parentheses because I'm not actually calling the tool here, I'm just indicating that it is tool 1, and I also put in there that it is a 19/32 drill. But following that are 4 variables to set the length, diameter, and various other things here. And you see that I've done that for the 3 different tools that I want to set. And let's talk about what these variables are here. So the 51, 801, 802, and 803 are the approximate lengths. And by approximate here, we can go plus or minus an 1/8 inch pretty easily and not have a problem. And if you're a little nervous about doing this, you can always estimate long, and if it has any kind of problem at all, it's that it never found the tool and would alarm out and saying, hey, I never found the tool. And then you would just decrease this value. So if this was a little long, I could decrease it. So approximate length, approximate diameter, that edge measure height, and the probing method, which we saw earlier. So we can have a bit of code here all ready to go to fill in all these approximate values. And it might look something like this. So we might tack this on at the end of our program. So here's my M30, and everything above the M30 was my part program to machine that part. And then right after that, I'm going to make an N9000, and it could be whatever you want here, but I'm choosing to go N9000. And I'm saying this is my tool data. And I have that same bit of code in here that I showed you earlier. I'm also indicating that with an ellipse down here that this could be not the end, there could be much more. And in fact, you might want to have one set of these for every tool that might run in your machine. So if you have a 30 tool changer, then you would have maybe 30 tools here, and just zero out the ones that you aren't going to use. So you can have this all in here, and then when you're going to set up the machine, you would just put the program in, put your part program in, jump down to N9000, and then run the program there. It'll put all of the data into the offset page, and then all the operator really has to do is press tool offset measure, and he can set, in this case, a single tool. So almost couldn't be easier here. And as I was putting this together, I was thinking about when I first started doing anything with the Haas machines, the tool offset measure was a really helpful tool at the machine because you could touch off with a shim or a gauge or something, and you would press tool offset measure, it would put your offset in, and then you could hit next tool and it would go up and index to the next tool and then load that and repeat. But in this case here, now tool offset measure actually uses the data that we put in and allows us to touch off a tool at any time we want using probing. So I would just initiate it, and I could even go get a wrench or parts or whatever while it's touching off tools. So it's a really handy way of operating your machine so that no one really has to ever set tools. It's already all ready to go. All right. So I'm going to switch gears now, and we're going to look at counters a little bit more. But first, we're going to look at what we did in the previous webinar, where we made a part, and I was mostly showing you probing, but I'm going to show you the machining part of that real quick here. So it drills one side, it drills this other hole. So simple part just to kind of use as an example. And here I've chosen to just put this block of material in a vise and run just one part. But maybe that's not really what I want to do. That's not very efficient. Maybe I have a whole lot of these to do. I would like to set up some kind of a fixture. I'm going to rethink my work holding, and I'm going to put parts in sort of like this, where I have 3 parts in a row or maybe more, but I'm going to determine that they're 4.5 inches apart. And I'm going to call it P1, 2, and 3. And I'm actually going to use the P1 as my offset. So G154 P1, maybe you're familiar with. We're going to use P1 for the first part and 2 and 3. But I know that these parts are 4.5 inches apart. So we'll circle back to that, but this is kind of how I want to set it up. So next, we're going to look at, this is the code. So this is what you saw run earlier. It calls up tool 1, drills tool 2 in mills, and the tool 3 then drills the other hole. And I put this in a box. So this is part of the concept of subroutines, is that we start thinking about code in segments, that we can capture that bit of code, put it in a box, and give it a name or a label of N100. You see at the top, I've highlighted that as yellow. I'm calling this whole thing N100. And I'm going to take it and shift it over to the side here and show you that all I'm doing here now is, while yes, this N100 in the box where it says machine the part, I only have that in there. I'm making this an abstraction of all this code over here. And this is just to simplify so that I can talk about the parts that we're going to add here, the actual macro part of this. And we're going to make a counter so we can machine these 3 parts. And we're going to start with pound 1 equals 1. And in this case here, I'm using pound 1 more or less as an example. It's the first variable really that I can use in this fashion. So I'm just going to use that for simplicity reasons, but any of the variables that are available to us, any of the user variables could be used in this case. And in this case too, I'm also using a local variable, which we'll talk more about a little later. Okay, so first we're going to initialize. And through initializing this, making pound 1 equal 1, I'm making sure that it's going to be the value that I want it to be. It may already be 1, doesn't matter. I want to make sure that I set it to the value that I want it to be. And you can think of this pound 1 as containing the number of the part that I'm about to make. So here's pound 1, and I'm going to jump down here to the N100 and machine the part, which follows right behind this. I'm going to run this, and I will have made the first part. Once I'm done with that, we're going to say, okay, now let's get it set up for the next part. So this is an increment. We're going to increment this. So we're going to make pound 1 equal to whatever was in there previously, 1 in this case, add 1 to it, and we'd have 2. So this is our counter. Next, we're going to get to a line that's maybe you've never seen before. And so we're going to talk about this in some detail. It's an if statement. And the important part of an if statement is that it is a conditional statement. There's an if, but there's this section that's in the brackets, and this is the condition. Basically what we're saying here is if whatever is in the bracket is true, if we can say this is true, then we're going to do whatever follows that. So in this case here, if this is true, we would go to 100, which is back up here to the N100, and it would machine another part. But let's look at the conditional statement a little closer. So here we have #1, and the LE part of this is less than or equal to. And let's take a look at different logic statements here. So we have various different possibilities here. We have 6. We either can make it that whatever is in the first part of this conditional statement is equal to 3, then it would be true and it would do whatever follows, or not equal to, and so on. I've included the 2-letter part of this, what we have to do in our programming. It's like my less than or equal to that you see here at the bottom. And I've also put in parentheses the mathematical symbol that is equated to the 2-letter representation of it. And then some examples here of what we can do in this conditional statement. So first of all, just like what you see up here, we can make a variable equal to or whatever, one of the logic statements. If in this case, if #100 is equal to 3.1416, then it would be true and it would do the next part. We listed the variable first and then the constant. In this case here, I'm going to put the constant first. That's okay. I can put the constant and then put the variable at the end. Or I can compare 2 different variables to each other. Is #1 not equal to whatever is in 5221? That sort of thing. I can also do a little bit of math in here too, so I can take whatever is in #1, take it times 2, and see is it greater than whatever is in #500. So these conditional statements can get rather complex if you wanted. I tend to try to keep these as simple as possible, but if the math does make you have to make it complicated, it may happen. But this is what you have to do to produce some sort of conditional statement. The big thing is that you really should always be checking a variable either to a constant or to another variable. You're not going to do is 1 equal to 2, both constants. That makes no sense. It's never going to be true. So you always want to compare a variable to something. All right. And then another example here is what follows. So we have the conditional statement, but what happens in this case here, I'm saying go to 100, jumps back up to the 100 line. But maybe that's not what I want to do. I want to do something else, like maybe if this is true, then I want to turn the coolant on. So this is how I would do that. So anything other than go to, you put a then, and then it'll just run whatever is after that. Another example is I can make it move somewhere. It could be any kind of regular line of code that you would have in a program. And of course, we can also do something that's macro too. We can make, in this case here, all we're going to do is make #2 equal 1. So it gives you a little bit of an idea of what can be done with these kinds of statements. We won't go any deeper into that, but just kind of give you a little hint of that. And then back to this. So we have this bit of code in here, and there was a problem with this. Previously, I had G154 P1. In that case, it would have done just like what you saw. It would just drill and machine just one part and do it 3 times. But I don't want to do that. I want it to run 3 different parts. So what I'm going to do here is I put P #1. So the first time through, #1 is equal to 1, so this would be P1. But the second time through, it would be P2 and P3 and so on, however many parts that you want to do. So this will call up the other work offsets. So it's already set up to handle that. It's an important alteration that I must make to my program. Okay, so we'll take a look at this, how this looks, and we'll run this. So this isn't showing 3 different parts, but gives you an idea that we'll run one part, and then the second part, and this would be in a different location. And then we move to the third part, and oops, there's a bit of a problem here, isn't there? I don't really want it to change tools as often as it's doing here. So this is a problem, and we'll have to think about this. How do we fix that? Well, let's come back to that. Let's take care of one other thing. So what about setting our work offsets? Let's take a look at that. So we looked at this earlier. We had our 3 parts up there, and we called it P1, P2, and P3. And we know that they're 4.5 inches apart. How do we set the other work offsets? Well, if we only had 3 parts, we might just probe all 3 parts and be done with it. But if I had 10 parts, then it's going to start adding a bit of time, and it's like, well, would it be nice if I only had to probe 1 part? I know they're 4.5 inches apart, and my fixture is very well made, so I know that they're 4.5 inches apart, and that's not a problem. So how do I do that? Let's take a look at that. So up here, I have a few lines of code, and 14,001 is G154's P1X work offset. And in this case here, I'm going to make it equal to 15.8001. Now, I'm putting this line in here as sort of a representation that somehow or another, I've got to get a value in 14,001. Maybe that's done through probing. Maybe I don't need this line of code, but it's just representing that that would go in there somehow. But I don't want to probe 2 and 3. To set the X coordinates of 2 and 3, I'm going to just do some math. So 14,021 is G154's P2's X work offset. And all I'm going to do is I'm going to take the 14,001 and add 4.5 to it, like 4.5 down here. And then 14,041, I'm going to take the 14,001 and add 9 to it, so the 4.5 times 2, and that one's P3. So I'm setting these values by just putting a bit of code in my program to take whatever is in P1 and transferring it over into P2 and P3. And let's take a look at these numbers that we have. So this 14,001, 2 and 3 are the XYZ of P1. 14,021, 22, 23 for P2, and 41, 42, and 43 for P3. So I can set X, Y, and Z. So up here, I only was setting X, but Y and Z for these parts are going to be the same. So what I can do is I can actually put in that 14,022 is equal to 14,002, and likewise 14,042 also equal to that same one. So this way I transfer the Y and the Z over to these other guys, and I do this math for the X, and I've got all my work offsets set. And if you have quite a number of parts, this is even more powerful. The more that you're doing, the more that you're repeating, the more powerful this actually can be. Well, let's take a look at the problem that we had and my solution to this. So the problem was I was trying to fit too much into my box. So I had an N100 box, and I just took all of my programming, all of my part program, and stuck it in that box. So I did too much. What I need to do is break that down tool by tool. So in this case here, I'm doing exactly the same thing. I initialize my variable here at the top, and then I move into position with the appropriate P number, also parameterized with the #1, moving into location. And when it does this, it's in a G81 cycle, so it'll drill the hole there. And then I can increment, just like I did before, and test. If it's true, go back up to the 1. And I want to bring up another thing here too. So the first time through, it's 1, then it becomes 2, and at that point, 2 is less than or equal to 3, so it'll jump back up, run another part, and then it'll make it 3, and then we test again and we see that it's less than or equal to 3, so then it's going to jump again and make 3. And then at that point it becomes 4, which in this case 4 isn't less than or equal to 3, so it will just continue on. Where we would jump to the next part, or next tool, and reinitialize, and do a similar thing here. Exactly the same sort of concept. And then finally on the third tool. So I just have to break it down per tool instead of trying to dump everything into one section of code. Another thing that happened in here, and we talked about it a little bit before, was that we have the #1 is in this P value. And what I want to let you know is that we can do this with any letter except for O, which is our program number, and we can't do it with N. So we can't have N #1. That's not acceptable. The program would alarm out if you tried to do that. But any letter, G codes, X's, feed rates, any of these will allow a variable to take its place of the number that normally would go there. It's a very powerful bit of programming by allowing us to make this line of code work differently depending on what the variable is set to. And then one other thing that I neglected to mention was if we go to run this, the machine looks ahead. Normal programming is that we want look ahead. We want it to read ahead of itself. But what that means is it could look at this and actually count all the way to 3. And so we might only run the third part here instead of the first and second. To fix this, we can put G103P1 at the top. And then all of this will have no look ahead, only run one line at a time, and it won't count ahead. This is a common thing to put in a program. If you're going to be doing some macro programming, you may need this in your program. But I also want to point out that if you're going to use cutter compensation, you can't have this on. So you have to kind of work on that to plan, well, how can when do I need to have it not look ahead, and when do I need it to look ahead? So you only really need look ahead for your cutter comp lines. Okay. And just a few things about blocking the look ahead. The G103P1 is one way of doing that, and it's sort of a global thing. So when I put on G103P1, it's going to stay one block at a time until I put another line somewhere that's G103 by itself. This will put it back to full look ahead, which should be P15 in that case. It would put it back to that, and then you're back to normal machining at that point. Also, what blocks look ahead is M1 or M0. Those also block it. So I'm going to go back one slide. So the M1s that you see here are making it, and these two here, I'm making it so that it doesn't go past that. So it'll only work the look ahead. If I didn't have this 103 here, it would only affect this tool because the M01 will block that. And you don't have to have optional stop on to make that happen. It's just it will not allow the look ahead to go further than the M1. And another way of doing it is using the block delete or the slash. You can put those in on lines as well. So again, back to this line, if I put slashes in front of everything here, that would also do the same thing. Okay, so those are important to understand, that you have those tools available to you as you are building your programs. Okay, so next we're going to look at a little bit more of the nuts and bolts of things. We're going to talk about really the two parts to macro programming, which are subprograms and variables. And you may already be familiar with M98 and M97, the global and local subroutines. G65, which we've seen a bunch of as we went through these webinars, that we were using G65, and the big difference is G65 is very similar to M98, except for it allows us to use what are called arguments. Basically what that is we can pass information into the subroutine, and we've been doing that. I'm going to look quickly at some probing cycles. This is where we've been using them. And on the left side, I've got the G65 P9995, which you have seen a bit of. This is what we get when we use conversational programming. And the A that we have on there, I'm leaving it blank here, but the A is actually a process of identifying which cycle we actually want to do, whether I want to touch off a tool or if I want to do a single Z offset in a work offset or whatever it is that I want to do. The A is what controls that. And if we go on to the next one here, we look at the local variables. So when I say A10 in this case, when I run program 9995, right out of the box, as soon as it starts running, #1, which you see is associated with A, will be equal to 10. So this bit of information, this A 10-inch or 10, whatever it is going to jump into my 9995 program, and I have that piece of information now, and I can have that do whatever. I can have it jump to a part that touches off a tool or something. Whatever this A actually does, there's maybe if statements in the 9995 program that make it jump to the part that handles touching off a tool. Okay. So I've got this chart up here, and you can find this in your machine manual. And I'm really primarily concerned with what I have highlighted here. So you see that I have virtually every letter represented here. I have all these variables, and you see that I have some that go beyond what the alphabet goes. These are all the local variables. Local variables are available in whatever program is currently running. So when I'm running my main program, I have a set of local variables for that program. And when I jump into a subprogram, I have a new set of local variables that are going to start fresh when I run that subroutine. They're local variables. When I jump back to my main program, the local variables I had previously set when I was running my main program will return. So if I had set some values, all that stuff is going to come back to life inside my main program. So this is kind of a handy thing in that I have a set of 33 variables that are only available to the program that's currently running. That's what local variables do. The letters that you see here, we have almost all of them. The only ones that we're missing is we cannot use O. You're not going to see an O because that's a program number, and that's the only thing that's used for. We won't see an N because we can't use that because we might have an N code that we want to have in the front of this line. We can't use G because we're already using G here, and we can't use P because we're already using P here. So you'll see that it's those letters that are missing. from the list here. And I also have grayed out these other ones. This is another way of doing it. I'm not going to go into that. This is less commonly used. This is more important if you have literally that much data you want to transfer over. In my opinion, the letters that you see that are individual, not repeating IJK, are much more appropriate. I understand what the letter means maybe, and I can understand what it is that I'm doing. But if there's several I's and several J's and several K's in a line of code, that gets confusing. So I recommend the ones that I have highlighted there. And then of course, all these other variables, the 27 through 33 as an example, are still available for use. It just doesn't pass information across in a subroutine call. All right. So what I want to do here is take a look back at what we did in the second webinar. So here's a bit of code that we ran where we did the top center of the block. So it's going to come down and probe this right in the middle, and then it'll do an X and a Y web. And that's what we see here. So this particular line here, 9995, the W54, this is our work offset that we're going to set. And this line does the single Z surface. When we're done running that, we have to turn the probe back on. You can see that that's the same code up here. And then we'll do the center of a block, which is what this code does here. And because this came from conversational programming, I'm not really worried about exactly what it all means because I'm just getting it and plugging it in and using it. The difference is that when I do it this way, every time I get done with a 9995 line, I have to turn the probe back on to do another one. So that's an important part of that, which we talked about in the second webinar. So this is the way we did it, and we'll run that bit of code. So it's going to drop down, and so it's running this first line here with the H, and now it's running this line. So easy, right? We had our template program, which teaches us how to call up the tool that we have to turn the probe on, and we want to use safe moves that you see here with the 9810. So it kind of teaches us that with the template, and then really it's just a matter of plugging in what we would get in the MDI page into our program so we can get what we want. Downside to all this is that I have to turn the probe back on. So every time it runs, if I had a bunch of probing to do, every time it runs, I would have to turn the probe back on, which does add time and uses a little bit of battery power, I assume. So let's take a look at it. We're going to convert that to this. And now I'm using the Renishaw programs more directly. And if you remember at the top of this webinar, I mentioned that you can get a book through a simple Google search. You can get that book and then it lists these codes. So I have this 9811, which is a Z single surface. So it'll probe right down onto the top. And then I have a web, an X web. So it'll do the two sides here. And then finally a Y web doing this way. So this is how I would rewrite that. So very similar, except for I now don't have to turn the probe back on. So probe comes on, stays on until I'm all done, and then I can shut it off. And this line may have seemed unnecessary with the other one, but I go ahead and include it anyway. It doesn't hurt anything to run it, because if it sees that it's already off, it'll just leave it off. But I put it in here so we can have it ready for this one, because in this case, if I didn't turn it off, it would just go ahead and put the probe away, calling up the next tool or whatever. And meanwhile, the probe is in the tool changer, flashing away that it's still on. So this is an important part of this one now, that we turn it off, because These cycles do not shut it off. Right. So another thing that's a little different here. Previously, we had a W that represented the work offset. So I had a W54 in the conversational programming that we created. Now I've got S1. Well, the S1 actually represents G54. And let's take a look at that. So I got some code over here, but the offset that I want to set, 54 through 59, if I was using P9995 through using conversational programming, it would be producing this W that matches the G that you have over here. But when we use Renishaw cycles, we must use S1 through S6. So 1 represents 54 and so on. So in my little example over here, you see that I have it highlighted that I'm in G54 at the beginning. That's how I do my probing, but I'm setting S2, which is G55. So this bit of code is using the work offset that was already there, we already had, and resetting another work offset, G55, to do a single surface and then a hole. And this is another part of this is it kind of important to understand here is that I don't have to set the one that I'm using. I can use something else and set a different one. And I've actually used this quite a little bit where I'll have a one work offset that is specifically for probing, that it's there so I can get, I can always use that same work offset for my probing, but I set a different one that I use for machining. Okay, so this is the 54 through 59, and you're probably familiar with it. You have more work offsets than that, and currently what's commonly used is the G154 with the P, and I had that in my earlier examples. So if this is what I want to set, the 154P1, if I was running the 9995, I would have W154.01. So the 0.01 is the P. Don't put 0.1, that would be the same as P10. It has to be 2 digits, so 0.01 for the P1. And likewise for the Renishaw cycles, you can put S154.01. I'm going to caution you here though, is it depending on the vintage of your machine, you might not be able to use this. You may have to use something else, and you'd have to look at what's actually available on your machine. On the older machines, there was a way to look that up. But on current machines, this is what you would put in. Okay. All right. So now this is another example, and this is using the 9995, the conversational version, and you see that once we probe our Z, then we have to turn the probe back on to do some safe positioning, and then our final probing, which is to find the center of that hole. So here's what that looks like. So that's what we had in the second webinar, and here's how I'm going to change it. So very similar to the previous example, we still have a single surface. I'm setting G55 here. I don't need to turn the probe back on, just like what we had before. I do my same stuff, repositioning, and then I do a bore. Turn the probe off and I'm done. So it kind of gives you a little idea about that. While on one hand, it's pretty easy to use the conversational programming to produce the code that we need, but there is another way to do it, and it's a little faster, and probably saves battery power. But now we're going to switch gears a little bit, and I'm going to show you global variables. We've talked about local ones. The global ones are available to us by all programs. All programs can read the global variables. That's what the global means in this case. And I've kind of split it up here, so showing the classic control at the top and the next gen control on the bottom. And on the old classic machine, we would have 500 variables available to us, which is really quite a number of them. We're in the 100s, what I call the 100 series, the 500 series, the 6, the 8, and the 9. Okay, so this is what we had, and it was just 3 digits long, like this. But on the next gen control, they added a 10 to the front of that, basically. We put a 10,000 and whatever after that. And what it does is it opens up the one starting with 0 up to 99, and it opens up 200s, 300s, and 400s in a sense that we didn't have available before in the 700s. So it opens up a bunch and actually gives us double the variables. We had 500, now we have 1,000. I don't know that you need 1,000 typically. I would say in most cases, you rarely need much more than, say, 20 in a lot of cases. But it's nice to be able to have it open more in case you run into that project that does require a lot more variables than what you imagined you would ever use. But we also have to talk a little bit about what's off limits. So I'm going to gray out the ones that I don't want you to think about using. So if we're starting with the classic control, if this is what you have, you don't have a next gen control, then I would say that you're going to start using variables at 600. So you can use the 600 series, the 8, and the 9. Okay. And the deal here is that some of these variables in this 100 series and the 500 series are being used by the probing system. And let's take a look at this first one, the 100 series, for a second. So in here, there's some calibration stuff, but the 185 through 180 or 199 are probe output variables. Again, this is something you would find in the Renishaw book that I mentioned. And I'm only listing this as the 185 through 199. In here would be 10,185 and 10,199. Although you can still write the program using just like what you see here, 185 to 199. You don't have to put it as 10185. So this is at the top, we consider these legacy variables, and we can still use legacy variables in our next gen control. Benefit to typing in 100 instead of 10,100 is that it's just less typing. And if you're already used to looking at these, when you look at this one, you might get confused by this. So if you're familiar with using these variables, I myself still continue to use the legacy ones as much as possible. Also in part because anything I develop would be able to run on older machines as well as newer machines. But these probe output variables, I'm going to give you an example here of that 188 is the size of a bore, web, or pocket. So anything that has a size, if we probe something that has a size, like for instance a hole, we're going to get that information fed back to us in the macro page, and it's going to be under 188 or 10,188. It's going to show us that size, and I want to show you a nice little thing you can do. If you go into current commands, whether you're on a next gen control or not, you can find the timers. You just page through and find this timers page, and you see that I have macro label 1 and macro assign 1. So under macro label, I put in size because that's what 188 is, and I put 188 in here. And then if I look at my timers and counters, I will see the word size here now. And whatever the last thing I measured, it'll show what that is, what that value was right here. And this can be very handy for when you're running the machine if you want to just probe something to figure out the size of it. Like you've just machined it and you want to know, is that right? You can just go into conversational programming, go ahead and probe something, and it will, when it's all done, it'll tell you what the size is right here. So you don't have to go hunt for that variable. And you have two of them, so you could set up something else if you want to. But for me, at least, I like to put size in there because that's a pretty handy one. And then back to this, the 500s are another one that I encourage you to avoid because this is where calibration information is stored. Now, there are values, or I should say variables, that are in this section that are open to being used, but just to simplify things here, I can tell you that if you avoid the 500s entirely, then you won't have any problems. This is why with the classic control, I always suggest the first variable that you can use is 600. Of course, on the next gen control, it can be any of these other ones, just not the 100 series and not the 500 series. Okay. And then other thing here is to talk a little bit about system variables. We have seen these, so I just want to touch base on that a little bit more, is that system variables are things that we can potentially write to or maybe just read to see what's in there. Some variables, some system variables are read only, so I can't actually put a value in, but I can see what's in there. So the machine's putting values in there for me to look at, but not for me to change. But system variables are at least one of the most powerful things that you can use. Is all tool and work offsets all have a variable attached to them. So I can write to any offset that I want, and that's pretty powerful. So I can set things, I can change things if I need to. I also list tool data there because we looked at that early in this webinar, that the tool data is stuff where I can set the approximate lengths and diameters, so I can provide a nice, easy way for the operator to just jump into the offset page and tool offset measure, and I've got my tool being touched off. We looked at timers and counters. That's part of the power of macro variables, is be able to look at those counters and use those. And then we can also create our own alarms, which I'm not really covering in this webinar, but pound 3000 is our a user alarm, so we can actually create an alarm, like if something happens or if a value gets too big or too small, like let's say you probe a bore, you can look to see if it becomes oversized, we can throw up an alarm so the operator knows something happened and the hole was machined too big. So that part's ruined. We want to alert the operator before another part gets made. And there's much more. So this is also going back to the the manual on your machine. You can look up system variables and see what all you can actually access. So something that's quite powerful. Just to kind of close things up, I want to talk briefly about a couple of what I'm calling kind of honorable mentions. There's stuff that you cannot do with conversational programming, but are readily available to you right now if you just write the code yourself. So let's take a look at a couple of examples of that. One of them is 3-point bore, or boss. If I have something that's a not complete circle, or at least not complete at either 0, 180, 90, or 270 degrees, any of those quadrants of a circle, if those points are not available to me, example, what if I have a keyway in a hole? If there's a keyway in there and it's right at where 0 angle is, then can't probe that with a regular 4-point. So the 3-point allows me to go in there and specify the angles, and that's what the A, B, and C are here. So A is going to be the first one that it does, then B, and then C. Okay, so I'll run this. You can see what that looks like. And 0 is at the 3 o'clock position, so it does that one, second one, third. This is also faster, but may not be quite as accurate. When I say may not be quite as accurate, it's still pretty accurate, but the 4-point often is a better way to go. If you can use a 4-point, probably just go ahead and use a 4-point. But the 3-point can be very handy in certain situations as a problem solver that I can't measure it, or maybe it's a cast surface or something, and that's right where the parting line is, and that's not representative of where that hole is. A 3-point might be able to get me past that. So 3-point, and another one is feature to feature, and I'll run that one. So on this one, it comes down and it's going to bore the hole. And then you can see over here, I have it save data. So this 9834 is saving the data of where that hole is located. Going to reposition, drop down, and it's going to do an X surface. And when it probes this, after it probes this, I run another feature to feature code. This is the exact same code as up here where I saved the data. And I'm saying, well, it should be at minus 1.45. And if I look at pound 185, I will get that distance. And maybe I'm looking for it to be 1.45, but maybe it measures at 1.5. So I can see that value. I can look up in 185 to see what that distance is. Okay, so that's a pretty cool one as well. So now just a few things just to kind of review. We talked about auto tool setting, and I really want to emphasize the fact that auto tool setting in the way that I described it earlier is very powerful for the operator, so that pretty much anybody can set a tool by just hitting the tool offset measure key. We looked at counters, and counters are something that are very powerful. In my example that I gave, I was counting parts essentially, and that could be done with the M30 counter, that 3901 that we looked at earlier. But by making my own custom one, I can look at counting any number of things. Like in my final fix there, I counted how many times I used one tool, not how many parts have I been making. We looked at conditional statements. So we looked at kind of how that works, that we have an if statement with some kind of a condition in there where we're comparing a variable to some other variable or some other value to see whether we want to do one thing or another thing. We looked at system variables enough to know that we can adjust offsets. We understand arguments, so this is the information that we're passing into a subroutine. We looked at types of variables. We were looking at local variables, which are those arguments, and we looked at global variables and system variables. And I guess I want to point out here is that system variables are what the machine is using, and the global and the local are ones that we are using to control the machine. So in a way, there's sort of the separation of user variables, the ones that we're controlling through the local and global, and then there's the system ones, which are generally speaking more powerful and controlling the inner workings of the machine in many respects. We looked at converting from the VPS to Renishaw cycles, which is basically bridging you into a whole new world of programming where you're using the Renishaw cycles more directly. And I would encourage you to work in that direction. It's nice to get kind of get your feet wet with the VPS, But as you get better with that, I would suggest that you get into these Renishaw cycles, and in part because of these two guys. The 3-point bore is not possible with VPS, and neither is the feature to feature. All right, and just one more time with this, I'm just going to put this up here, so if you didn't get it earlier, if you're looking for this manual, I suggest a Google search, Haas Renishaw Programming Manual, and that you should also look through your macro section of your machinist or your machine's manual to learn more about the ins and outs of probing. And if I didn't mention it earlier, remember that we do have classes on macro programming, and I would encourage you to join in one of those. And that's it. Hope.
Okay. So we're going to get to the questions. We do have a few here. Dave, does the next gen control no longer need G103 P1 to limit block look ahead?
As far as I know, we still need to use that. If you are witnessing that maybe you don't need it, then that's new for me.
This question came up before you mentioned G103, Dave. I think that's where it comes from.
Oh, okay. Okay.
Thanks, Bill.
All right.
Okay. Carl is asking, if you were to probe a bore or hole that had a keyway at 90 degrees, is there a way to do a 4-point probe and rotate it 45 degrees to make the machine probe at 45, 135, 225, and 315 degrees and miss the keyway?
No, you need to use the 3-point one that I showed. There's no way to rotate that. Before you go on with that, I should point out that you can't use things like rotation, scaling, or mirroring if you're using probing. Okay.
Okay. So it looks like there are no other questions at this time. So I'd like to say thank you today for our presenter, Dave Nelson, Applications Engineer from Productivity, and Bill Schnitger, also Applications Engineer from our Omaha office, for helping to answer the questions in our Q&A. And again, we thank you all for taking the time to join us today. Join us for our next webinar, an introduction to right angle head programming, presented by Brent Nagel, Applied Sim Technologies, on Wednesday, August 12th. We hope you enjoyed today's webinar and look forward to seeing you again soon. Until then, stay safe, stay healthy, and thank you for your business. Have a great day.